Hello, I am Pierre Godet and I will present a new deep learning-based algorithm for multi-frame optical flow estimation. This work has been done at Onera and is also supported by the French Agency of Defense, DGA. Optical flow is the displacement field giving the apparent motion of every pixel between two frames, and it looks like this. So this is what we want to estimate. Our work mainly builds on two previous pieces of work. IRIPWC, a method based on a convolutional neural network which iterates on the same weights for the different levels of a multiscale estimation process, and continual flow, also a CNN method, which proposes a recurrent multi-frame estimation process by giving the optical flow estimation from the previous time step as an input for the next estimation. Our method is recurrent both in space and time. It is based on multiple calls to a SpatioTemporal Recurrent cell called STaR cell, represented here by the white squares. If you read this figure from left to right, you can see the multiscale estimation process for a pair of images. As IRIPWC, our method iterates on the same weights for the different levels of this multiscale process. Our method also estimates occlusion maps jointly with optical flow. This improves the optical flow estimation. Now if you read from top to bottom, you iterate through the different time steps of a video. As continual flow, we implement a temporal recurrence represented by the red arrows. By doing so, our networks accumulate information from the past. Our method uses a unique spatiotemporal recurrent cell for every scale level and every time step. This is how the STaR cell works. What I want to underline here is the main difference between our method and continual flow. While continual flow conveys the optical flow estimation from one frame to the next, we rather use a learned feature map that is given from one time step to the next, as shown in red, and that acts like a memory state that accumulates information from the past and helps estimation process in the future. Another difference with previous work is that unlike IRIPWC, we use the same weights for optical flow and occlusion estimation in the whole network, except from the very last layer. At paper writing time, our method gives state-of-the-art results, ranking first on Sintel final and on par with IRIPWC on Kitti. The last column shows that STaRFlow is lighter than competitive methods. A more detailed comparison, including more methods, is available in our paper. Here is a result on Sintel, where we can compare IRIPWC, continual flow, and our method STaRFlow. First, we can see that a multi-frame process helps to estimate motion in partially occluded regions. This is the case on the knee, occluded in the target frame, which is well estimated by the two multi-frame methods, continual flow and STaRFlow, but missed by the two-frame method, IRIPWC. Second, we can see that STaRFlow provides a better estimation on fine spatial structures like on the hair or on thin objects, compared to both related methods. This shows more specifically that STaRFlow can estimate the motion of small and fast-moving objects. While the two-frame method based on a very similar architecture, IRIPWC fails to estimate the motions of the knife, STaRFlow provides a very good estimation. Finally, here is a result on real-world data filmed with a smartphone. STaRFlow performs really well, while this result is obtained with a model trained only on synthetic data. Compared to the two-frame method IRIPWC, our estimation is cleaner, in particular on small objects like the balls and the hands. So, to conclude, we leverage temporal coherence by implementing a temporal memory able to accumulate information from the past. Using learned features in the temporal recurrence allows better exploitation of temporal information than propagating optical flow estimates as proposed in continual flow. Our multi-frame process improves optical flow estimation at occlusions and on small objects. Thanks to weight sharing, as we use a unique recurrent cell for every level and time step, our network has a lower number of parameters compared to other state-of-the-art methods. Thank you for your attention, and a PyTorch implementation of our method is available on my GitHub. And if you want to know more, I would be glad to answer your question during my poster session. Thank you.